Hello, and welcome to our ELECOMP Capstone Spring 2024 Summit video presentation. We are Team Zebra Amelia, and our project is the wireless enablement of green power technologies for edge devices, which has been nicknamed Project Amelia. Here are our technical directors, Joe Moreira, an engineering fellow, and Bradley Willard, an engineering manager, both from Zebra Technologies. They have provided us much support and guidance throughout the project. For our ELECOMP Capstone designers, we have 3 computer engineers, those being Andrew Wu, Alan Liu, and Eddie Perez. For the 3 electrical engineers, we have Alan Pawanski, Lucas Frost, and myself, Joseph Dyer. Nick Fedorenko is our double major, majoring in both computer and electrical engineering. Our sponsoring company, Zebra Technologies, was founded in 1969 and offers global computing printing technologies. Zebra specializes in printers and various other technologies used for marking and tracking. Their products can be found in several diverse industries such as retail, healthcare, and many more. The motivation for this project is to maximize the green energy usage in Zebra devices. Zebra devices, such as printers, incorporate a battery to power the device. These batteries must be recharged, and the scope of Project Amelia is to recharge these batteries when the renewable energy from a power grid is at its maximum. In doing this, we reduce the carbon footprint of Zebra devices and their consumers, as well as reduce the electricity costs for Zebra customers. This creation will help push Zebra towards becoming a leading company of green energy. The anticipated best outcome of this project is to create a subsystem that predicts the optimal time to charge the battery, that being when the renewable energy is at its maximum. The subsystem itself will require power, therefore we look to minimize the total power consumption of the subsystem so that the majority of that green energy will be used to recharge the battery. The subsystem will incorporate a dual Wi-Fi Bluetooth-based architecture, as well as a user dashboard and web app to provide the user information. We aim to conclude the project with a text fixture that reaches the pre-engineering validation testing levels. We have unfortunately not achieved our ABO, but we have put together a strong foundation that covers every aspect of the project. We have achieved a Wi-Fi and Bluetooth-based architecture that includes a Bluetooth Low Energy service and a web application. We've also completed the design of a battery analytics system that will collect and send the power-related information. The team's accomplishments are the selection of the power measurement method as well as the voltage regulator. A plan has been derived to minimize the total power consumption of the subsystem. We have selected a microcontroller that includes an internal Bluetooth system and a Wi-Fi transceiver. We will utilize a Bluetooth Low Energy service and a Wi-Fi communication. We have a non-volatile memory to hold data and a cloud service that will run the majority of the software applications of the subsystem. A web app has been created to display information to the user. The integration of this system to Zebra devices will make them more environmentally friendly, which will appease to several Zebra consumers as well as new consumers. Consumers will also avoid the economic activity of non-renewable energy sources, such as an increased cost of fossil fuels and/or coal. These integrated devices will reduce the customer total cost of ownership, therefore bringing in new Zebra customers. Here you can see a block diagram that summarizes the Amelia subsystem. Squared in red is the portion that I worked on, which is the power input of the subsystem. My name is Joseph Dyer, and I worked on the selection of the power measurement method as well as the voltage regulator. I derived the plan to minimize the power consumption of the subsystem, as well as I am the lead designer in the creation of the hardware layout and schematics. We look to minimize the power consumption of the subsystem. During the charging mode, when the battery is being charged, the subsystem will be fully functional to provide the user constant data of the charging time period. But during the standby mode, when the battery is not being charged, the subsystem will transfer into a sleep mode or shutdown mode, and in this mode, it will be low power, where the subsystem will wait for the next charging time period. During the standby mode, the system will perform quick interval bursts to check in on the battery. Since our system cannot directly recharge the battery, we put together a design to simulate the charging and standby modes. We achieve this by utilizing a load selection system that will utilize the charge enable signal to switch between the two modes. The cloud and Wi-Fi service would determine the best time to charge the battery. This would then send a signal to enable the charging mode. Otherwise, the system will be in the standby mode. Here is a visual layout design of the Amelia subsystem. This is the board that is capable of performing all required functions, such as the Wi-Fi and Bluetooth architecture and the battery analytics system. It contains every major component as well as interface headers. This will allow it to send information and data to other hardware components.
My name is Alan Pivoinski. I'm an electrical engineering major. For this project, I worked mainly on the hardware with an emphasis on the power input section. This involved choosing a voltage regulator along with a method of measuring current and voltage. To a lesser extent, I also did some research on the power grid and some research for choosing a suitable microcontroller for this project. Our project uses USB for power delivery, which delivers anywhere between 5 and 20 volts, but many components that we used require 3.3 volts, so we require a regulator to step this voltage down. We had the option between a linear supply and a switching supply. A linear supply would be easier to implement, but is less efficient, while the switching supply is way more efficient, but also more difficult to implement. Because of the power conservation goals of our project, we decide to take the trade-off and go with the switching supply, even with its higher complexity. To determine the power consumption of our system, we needed to measure the voltage and current that was coming into it. To do this, we had a choice between two devices, a shunt resistor or a contactless sensor. The shunt resistor is capable of providing very accurate measurements and is very simple to implement. Unfortunately, in certain situations, it can cause relatively large power losses. The tunnel magnetoresistance current sensor was our second choice for a sensor for measuring current. It is higher precision than the shunt resistor and is contactless, meaning that it doesn't have to be directly in line with the current that is measuring. Unfortunately, this comes with it being more susceptible to magnetic noise and also less sensitive to small currents. In addition to this, it would require an additional analog to digital converter that our choice of shunt resistor sensor didn't need. To decide which sensor we would ultimately use, we decided to run some tests. One of the tests that we decided to do was an efficiency test, where we decided to measure how much power the sensor was using while measuring different currents. While doing this, we discovered that in our case, the shunt resistor actually used less power, so that's the one that we ended up going with.
I'm Lucas Frost. I mainly worked on the cloud and grid data section of the Amelia system. So I worked on research for the electric grids, collecting data from the grid, and I focused on local grid generation this semester. So last semester, our approach with finding grid data was too general. We were getting hourly data from the entire U.S. One of our ABOs was that we should be able to sense data from the local grid. So we decided to find a new approach to do this. We ended up coming to this conclusion that we should estimate the green data ourselves using some sources and equations. So first we use a few sources to find solar and wind farms local to the area we specify, and then we have these sources that we get our data from. The wind power dynamite for the wind side of things, we have data on how many turbines there are, the make and model of the turbine, and the latitude and longitude where it's located. On the solar side of things, we have nral.gov, which gives the solar area, the solar field area. We also use data from a weather API and a few other sources to get more data necessary for our equations. And then we plug them into these equations. There's one for wind and one for solar to get the estimation of the power generation in the area.
Hi, my name is Eddie Perez, and I was a computer engineer working on this project, and my focus when developing this project revolved around the Bluetooth functionalities of the system, as well as understanding memory aspects and the real-time clock. To start off, I assisted with the initial selection of our Bluetooth manufacturer. We had received a recommendation from our technical directors, and weighing the pros and cons of different Bluetooth manufacturers, we ultimately landed on one that we used in our final design. I developed a custom Bluetooth low energy service specifically made for Project Amelia that is capable of displaying and sending out a variety of different information as defined by our ABOs, including voltage, power, current, and timestamp information. I successfully integrated and researched methods of implementing non-volatile storage, an external real-time clock, and an external voltage and current measurement tool. Through this, I was able to develop drivers that allow for easier integration into brand new applications should the need rise up in the future, and I was successful in making sure that any external measurement or anything read from the real-time clock would be stored in non-volatile storage and then sent out via the previously mentioned custom Bluetooth low energy service developed for Project Amelia to be read on an external device. I successfully implemented firmware over-the-air updates to allow for wireless updates of the firmware of our system rather than needing to wire the system in for receiving updates, which would be more convenient for the future. And then I successfully researched and documented methods for adding both connectable and simultaneous beaconing advertising to Project Amelia. This would allow for Amelia to advertise a Bluetooth advertisement set that would allow for an individual connection to an external device alongside a non-connectable beaconing advertisement set that broadcasts a set of predetermined information to be read by a observer device. Through this diagram, it shows the current setup of my implementation of the system, whether it's the external measurement peripheral and the RTC are hooked up to the development kit via I2C for read and write operations. These read values are stored into non-volatile storage to be read later, and when data is requested to be read via Bluetooth Low Energy, it retrieves these items from non-volatile storage and sends this out to be read on an external application.
My name is Andrew Wu, and I'm a computer engineering major working on this project. My focus is on grid data, the cloud, Wi-Fi, and the microprocessor. For this project, Microsoft Azure was the chosen cloud service, and I configured various services including the Storage Account and IoT Hub, also known as the Internet of Things Hub. Both were utilized for connecting devices to the cloud as well as storing data. I assisted connecting the microprocessor to the cloud by configuring all the necessary settings within Azure and gathered the necessary security information to implement in the code for the microprocessor. This would establish a secure, stable connection to the cloud. An API or application programmable interface was configured and utilized within Azure in order to retrieve carbon dioxide emissions, and that information would be used to help determine optimal charge times. I implemented a Python code that reads the renewable energy mix in the power grid to check when it will be at its peak in order to use less fossil fuels as a power source and reduce the cost of charging. I also assisted working on the web application in order for users to visibly view optimal charge times. So in this block diagram, an API initiates a request to the data source, in this case watt time, and it sends back a response with the requested information. Once the extraction is completed, the data is sent off to data storage, where it can be viewed and read in order to generate a graph that displays energy generation, lows, and highs for user analysis. In this block diagram, the Python algorithm assesses energy generation from both renewable sources and CO2. By applying a threshold value such as 30%, the algorithm compares the generation ratios to determine the output. If CO2 energy generation exceeds 30% of the total, the output is set for charging later. Otherwise, it's set for charging immediately. Additionally, binary signals of ones and zeros can indicate charge enable status.
I'm one of the computer engineers on this project, and I'm responsible for the microprocessor memory, watchdog timer, and real-time clock. So I worked with the non-volatile memory manipulation, and this is in the form of reading, writing, and erasing data from the non-volatile memory. I also worked with the watchdog timer configuration, and this is going to be used to reset the subsystem microprocessor in the event of a system malfunction or latch-up. I worked with the real-time clock configuration as well as the selection, where I selected the external real-time clock integrated circuit based on factors such as cost, ease of use, and low power consumption for our project. And this is to be used to keep track of the current time and date independently of the main system clock. And finally, I was tasked with the green energy mix, where I conducted research on electric grids and the ratio between renewable and non-renewable energy in various regions of the United States. So on the left here is a graphic representation of how the watchdog timer operates. So a timer is utilized to count down to 0, and if the timer reaches 0 without being reset by the microprocessor, the system will assume something is not functioning properly and initiate a reset or to correct the latch up. Our specific watchdog timer is set to periodically send a signal every 5 seconds and initiate a reset when 6 seconds has passed without a watchdog signal received. This time period is typical because the more time there is between watchdog signals, the more data will be lost during system malfunctions due to the increased time between resets while the system is down. On the right here is a graphic overview of a real-time clock. So a real-time clock will typically have a separate power source to maintain accurate time, even in the event of a power disconnection, as indicated by the coin cell battery to the right. This will be used in the Amelia subsystem for time-dependent information being stored in memory, such as charge times and power consumption in the form of timestamping. So this is a block diagram of how the non-volatile flash memory will be manipulated. We have code to first erase a sector in flash memory, then verify if the sector was properly erased. Next, an attempt to write into flash memory will be made, and lastly, verify if the values match what was written by reading from that memory location.
I'm Nick Fedorenko, and I'm the electrical and computer engineering double major who worked on this project. My main focus was to establish Wi-Fi communication between the microprocessor and the cloud server, as well as create the web app. My technical contributions include selecting and integrating the Wi-Fi board into the subsystem, establishing the MQTT messaging protocol between the board and the cloud, developing firmware for the microprocessor, assisting with cloud configuration, and lastly, developing the Project Amelia web app. For the project, we decided to use a thin client approach, which means all the computation and decision-making happens within the cloud, and the subsystem just receives a simple charge enable signal over MQTT to start charging the device. The device also sends battery information back to the cloud in a neat JSON format, which the cloud stores and presents in a user-friendly web app. Within the web app, we utilize WebSockets to receive the JSON battery analytics to then display it on graphs with corresponding timestamps. The web app also receives grid data in the form of CSV files from various energy information websites and APIs and presents the data onto the charts as well. Lastly, the web app determines when to send a charge enable signal back to the subsystem by waiting until the grid data reaches an ideal region to charge. For our key acknowledgements, first of all, we would like to thank our technical directors, Joe Morera and Brad Willard, for the exceptional help and learning opportunity that they have provided us. They were always keen to help with any issues that we face and provided excellent resources to achieve our anticipated best outcome. We would like to also extend our heartfelt gratitude to Dr. Sunak for providing us with this incredible real-world opportunity to collaborate with Zebra Technologies. This experience has truly given us a taste of what it's truly like to work as engineers. We are so grateful for this valuable learning experience. Thank you.